Welcome to the one more video where we're going to be talking about the famous fundamental theorem of calculus, part 1. Sometimes in your books you will see that we teach you part 2 first and then we're going to part 1. And this is what I'm going to do right now, but if your class teaches part 1 first, then it makes sense just to watch this video first and then go to the part 2. First, before introducing such an important concept, I want to remind you what does it mean to integrate something. For now, probably you're still thinking that it's all about finding areas under the graphs because we're torturing you with finding those areas using approximations with left endpoint, right endpoint, midpoint, and so on. But you'll be surprised that there's so much more applications of integration, and here is an animation that reminds you one of the very make sense application, which includes driving, speed, and distance. So if I want to find out how far did I drive with a different velocity, v of t, and v of t here represents the height of those rectangles, so basically I have a function of v of t. My speedometer recorded the speed of the car where I was driving from A to B. Then I know the time I was driving from A to B. So if I'm going to multiply the intervals of time, which are all the same or different, it depends on the problem, times the height of each rectangle, that gives me the speed for each interval in time. And sometimes the speed was slow at the beginning and the end, then the speed was very high in the middle. The product of speed and time gives you distance, which we know from school. So integrating velocity gives you distance. That means if I'm going to write the integral of v of t dt, which you can see at the top over there, that gives me s of t, which is distance. And that's just one of the applications of the integration. We basically have a hard problem, and then we're dividing into small, easy problems. And this sum of those many small problems gives you the approximate or even the exact result. And why the problem was hard? Because the speed was always different. How would you add millions and millions of different heights using rectangles or even a limit? So that's a cool idea here. One more point is that the more rectangles, the better result it gets. So when here we're saying that we're dividing a hard problem into many small problems, and each small problem can be calculated separately, and the sum gives me a pretty much good result. Here I'm reminding you that the more small problems we have in this division, the better the result is. And that's where the limit comes in. If the limit of those small problems goes to infinity, then the approximation becomes exact. And that's where the definite integral comes in, and the famous, fantastic connection happens between finding the area below the graph from A to B and finding antiderivative of the graph of the function you see at the top. Antiderivative of this function from A to B gives you a finite number, which is basically the idea of the definite integral. Now here's a genius question. Why we always keep looking for the integral from A to B, for the area from A to B, which is basically I'm asking you how far did I go from A to B. From one city to another city, what was the distance with the given velocity and the given time? Well, what if I want to keep going? What if I keep driving? Or what if my driving stopped in the middle? Can I change one of the endpoints? Can I ask the more broad question? What is going to be the cumulative sum of all those changes from A to unknown or from unknown to B? And that's the idea of fixing of one of endpoints while the other endpoints is a variable. You see this x running from left to right? I'm fixing A. A is 0. But x is keep changing. And I can stop x at any point I want. I want to stop it at 2 pi, and then it's going to be b. I want to stop it at pi, then it's going to be the middle point on the interval. Maybe I want to stop it somewhere in the random place. Then, this is a cool part of it. I can make x anything I want from A to B. Or maybe even send x to infinity. And those integrals you will learn in the future, which is pretty awesome idea, that what if I want to ask how far will I go when x goes to infinity? So my right limit of integration is infinite. That's a pretty cool idea. Well, if x is now not fixed, and that's my right endpoint, I can go as far as I want or as small as I want. Since x is changing and x is a variable, now my area is not fixed anymore. It's not a finite number. The more x moves, the more areas keep accumulated. So now we're gonna call this function area function, because now area will not give me a finite number. It will be some kind of function which will depend on the x. Where will I fix the endpoint? And this is how the topic starts. The topic starts with the introduction of the area function. The area function, I'll put it here. The area function happens when we're working with the continuous function for t greater than a. So as you can see, I'm fixing the left endpoint, but whatever happens after this is just on the right from a. The area function for f with left fixed endpoint a will have a definition, a of x instead of just a. So it's going to be a function of area now. The integral with the fixed left endpoint, and then the variable x, which is right endpoint of the function f of t dt. So this is what the animation was showing you. Look at this. I am fixing the left endpoint, but the right endpoint can go left and right everywhere I want, as far as I want. In the future, we're going to do x goes to infinity, and that will give me some cool ideas as well. Then this area is not a finite number like 5, or it's not 57, or it's not 57.3. Now it's a function because it depends on x. The farther my x is fixed, the more or less area is going to be, right? And that is why now we're going to call it a function area. A of x is an integral from a to x, where x is unknown, f of t dt. Why do we use f of t dt? We used to have f of x dx. Well, if you remember, this is a dummy variable, right? So it doesn't really matter what variable this is. I can do it f of j dj if you want that. But since we don't want these two to be the same, x and t means different things. T is a dummy variable, while x is actually important. It goes left and right, and it indicates not fixed right endpoint. So that's what used to be b, remember, from a to b. So now it's not b, now it's x, literally anything. That's why now we're using a new dummy variable t to make sure that those two are not the same. So from this definition, and the idea that the more I go, the more area will be accumulated. Check this out with the green color. So if my x goes to the right, this area will be keep adding. Make sense? And then it will follow the function shape like this, right? Or maybe x goes to the left. If x is over here, then only this area will be counted. So by moving x left and right, like a changing quantity, I can change area as well. And on this animation, going back, the interesting part is, what is this red g of x function is? G of x is this integral I'm just introduced to you. This integral is g of x on that animation. So the area now is a function. That means that the bigger the area, the function will be increasing. That's what you see on the animation. It's keep increasing. When the area shrinks to 0, the graph of the function goes to 0. If you remember that areas above the x-axis count to be positive and area below x-axis count to be negative, then when I'm counting area only on the left piece, the function in red, g of x, is increasing. But when I start adding negative areas, they start decreasing the total sum, right? Because the left area above the graph gives you 5, 10, 25. then after pi, the area becomes negative. It becomes minus 5, minus 20, minus 25. And at some point, it will balance out the positive area with the negative area. And that's why if I'm adding exactly symmetrical, the same area above the graph and below above x-axis and below x-axis, the final answer will be 0. That's why at the end, g of x hits 0. That's pretty cool. This is a function of sine of x, actually. Did you recognize that? And indeed, you can check that the sine of x, the integral of sine of x, from 0 to 2 pi will be 0. What I just said was that you can check that the integral of sine of x dx from 0 to 2 pi indeed 0. But the integral from 0 to x sine of x dx now is a function. And this function depends where my x will stop. Will it stop before pi, at pi, after pi, any place? And this is how the answer will vary all the time. Pretty cool. Let's go through several examples. What does it mean to have integral from 2 to x of 2x plus 3 dt? Well, that means that we are working, for example, with the area below the graph of 2t plus 3. And 2t plus 3 is a line. Here it is. Here's my line. And I'm looking from 2, and then my x is changing. It goes left and right. So my areas keep accumulating like this. Keep getting, and as you can see, since 2t plus y equals 2t plus 3, so my input is t, my output is f of t, and x is the right endpoint. Since y equals 2t plus 3 is increasing, then the areas keep increasing the more x is going to the right. When x goes to the left, the area is decreasing. Pretty cool idea. Well, actually here you can see that this is a trapezoid, right? And you can find this area either using geometry, which means you need to multiply by 1/2 the distance between parallel lines and the sum of those two heights. That's how you find area of the trapezoid. Or if you already watched the video with the fundamental theorem of calculus part 2, then you know what to do. You find the entire derivative of 2t plus 3. The entire derivative of 2t plus 3 will be 2t squared over 2 plus 3 instead of plus 3t. Instead of plus c, I'm doing bar, and I'll have from 2 to x, because I'm kind of treating this integral as definite integral. Since I do have limits of integration, it's just one of the limits is not fixed. So what is going to happen here is I'm going to plug the top minus the bottom. 2 and 2 cancels out. Plugging x is going to be x squared plus 3x. That's plugging at the top. Minus plugging the bottom. The top, I mean upper limit of integration. And the bottom, I mean lower limit of integration. 3 times 2. And the answer becomes x squared plus 3x minus 4 plus 6 is 10. So that's 10. Wow. The answer of the definite integral is not a number. In my other video, I said the answer for the definite integral is the number. But now you know, unless one of the limits of integration is not fixed, it's a variable. And that's what you call area function, because now it's not just a, it's actually a that depends on x. It's a that depends on x. You don't have to call it a, you can call it g of x, well, it's not f of x since f of x is reserved, m of x, whatever you want, but a is just makes sense to call it a since it's area. So it means that this area over here is changing with respect to the rule x squared plus 3x minus 10. It's a pretty cool idea. So the bigger my x, the bigger the area is. Indeed, if x is 100, this number will be huge. Versus the x is small, like 3. Then the area will be small over here, right? So here's a question for you. What will be this area if at I plug 2. What if this area is at 2? Before you plug it into the function, can you answer the question using geometrical understanding of what this integral means? Area of 2 actually means integral from 2 to x equals 2, that's 2, of the function which was 2t plus 3, 2t plus 3 dt. Do you know the answer right away? What is the integral from 2 to 2? That's basically we are moving from here to the same number here. So my x matches with 2. By properties of the integral from a to a or m to m is 0 because there is no area. It's just this one line, right? Since there is no width of the rectangle, then the rectangle area is 0. But check now by plugging this 2 into the quadratic function we just found. It's going to be 4 plus 6 minus 10, and that's 0 as well. That's a pretty cool idea. So maybe your brain is not handling it right now because there's too many things at the same time. But we just did 3 things in once. We checked what's happening with this area when the moving right endpoint matched completely with the left endpoint. It makes sense that this area then is 0. But since we knew the accumulative function, this is the accumulative function in this green box, for the area function, we could also just plug x, which is 2, into this function and find it indeed it is 0. And you can also plug, say, 4 and find out that area at 4 will be smaller than area at 10 or 100 because, as you can see from the graph, the more on the right my x is going, the more area I accumulate. And that's what you call accumulative function, accumulative area or area function. It always depends on the shape of the function. So here it is again, and as you can see, here they even show you how to find this area using geometry. If you did not watch the video with Fundamental Theorem of Calculus Part 2, then you can still find this area using geometry. And the area of trapezoid, even without finding an antiderivative, will be this area of x, will be 1/2, that's the formula. Then the distance between parallel lines, that's x minus 2. That's because the left end point is 2 and the right hand point is x. So what's the difference? X minus 2, right minus left, times the sum of the height of each parallel line. The right height is x plugged into 2t plus 3. So that's 2x plus 3 plus, and I'll put it in small parentheses. But the left height is actually given. You just take this 2 and plug it into 2t plus 3. That gives you 7. When you simplify this function, it gives you the same result, x squared plus 3x minus 10. Pretty cool idea. So either using geometry or using antiderivatives like I did over here. Antiderivatives and fundamental theorem of calculus. Find antiderivative, plug the upper limit minus plug the lower limit. Nice. Now, we can keep going with this idea that the area is changing and I have a question for you. Can you answer how fast this area is changing? How fast a of x is changing? Question mark. So what I'm asking you, it's definitely moving, right? So we found on that animation, the area is changing. We also tried different numbers, 8 of 4, 8 of 100, plug them into this box. You see it's changing. 8 of 2 is 0, and so on. So it's a natural question to ask, wait, if this area really represents something important, for example, it was a distance, right? Like we saw in that first animation. Or in my other videos, I showed you that if you have a graph of people got sick with COVID-19, then this area will represent total amount of sick people from the time we measured, time 1, time 2. So if I want to have a function that will tell me how many people are being sick all the time, then it would be nice to know how fast this area is changing, right? Then we know how fast the virus is spreading and whatever you want, any other application you think interesting about. How to answer the question? Here is my function a of x equals x squared plus 3x minus 10. How fast a of x is changing? I taught you before, if you see this phrase, how fast, that's usually a synonym of finding a derivative, right? So that's what I'm going to do to answer this question. So that was a question answer. I will find a derivative of a of x because that will tell me the speed of the function. Derivative of this function is 2x plus 3, right? But we had this function before. Look at this. The original function was 2t plus 3. That's exactly the function that was graphed over here as the line, and we found the area below this line, and the area was accumulative. So very interesting. Seems like when I'm gonna differentiate the result of integration, it gives me whatever we started with, but with different variable. We started with t, and now we have x. That actually completely makes sense. And that's not supposed to be a shocking thing. So we had area, that was area. By differentiating the area, finding how fast this area is changing, if this is the area function. Yes, area function. Because if area is a number, it doesn't make sense to differentiate the number gives you 0. But by differentiating the area function, it gave me the original graph of the function, or the function below which this area was found. It's pretty cool. So we're reversing basically the question. We used to ask you find the area below the graph, and now we're basically saying, can you find the graph with the given area below the graph? Make sense? So after we found this derivative, we can now finally introduce to you the famous fundamental theorem of calculus, which basically connects differentiation and integration into one step. Because going back, what did we do? We built the integral, it's over here, we built the integral from 2 to x of the function 2t plus 3 dt. That integral gave me x squared plus 3x plus t. Then I differentiated that result. So I found derivative of this function. I found d with respect to dx, that means x is the variable, of this integral. That means we integrated first, we got the result, the a function was x squared plus 3x minus 10. Derivative of that function is 2x plus 3. So the answer is 2x plus 3. That means we're putting together integration and differentiation. We're differentiating the integral. And that's a big deal and a really cool question, which could be asked, what's gonna happen if I'm going to differentiate the integration? So basically we're undoing the process, right? We're undoing whatever we did before. And this takes us to the fundamental theorem of calculus. And that's going to be part 1. That's the original one. So if function is continuous on the closed interval from a to b, then the area function, which now we know how it calls, a of x, is the interval with the fixed left endpoint a, but a variable right endpoint x, of the function f of t dt, and x is running from a to b, which is actually not very necessary. In probably Calculus 2 class, you will learn what happens if this is infinity. That will be super awesome topic. So this area function is continuous. That's a big deal. It means the area is not going to jump anywhere. And also differentiable on the open interval a and b. The area function also satisfies the idea that if now I'm going to differentiate this area, it gives me the original function f of x over here. So this is what we need you to know. If you want to differentiate the area function, that means you want to differentiate the integral. And when you're differentiating the integral with the variable upper limit, then you're getting the original function at that upper limit. So the original function used to be f of t, integral from a to x, and I'm differentiating this integral from a to x with respect to x, then the answer will have the original function, but with this upper limit. Upper limit. That's a pretty cool idea, that we're plugging in the upper limit, which means that the area function of f is the entire derivative of f on the closed interval. Think about it a little bit, observe the information, and just for you to compare, what is the fundamental theorem of calculus part 2? That's the one when we allow you to plug the top minus the bottom, or the upper limit minus the lower limit. So that's the one actually is more applicable. Find the entire derivative of the small f of x, and we're gonna call it capital F of x. Plug the top minus the bottom, and you got the result. That's the fundamental theorem part 2. And sometimes we start with this one, and then we introduce you what's gonna happen if we want to differentiate the integral with not fixed upper limit. And again, look at this cool animation over here. The upper limit, or the right part of the interval, is not fixed. So the areas keep accumulating. This area now is not a number, it's an area function. Since it's a function, we can differentiate it or even integrate it. What's gonna happen if I differentiate that function? Then it will give me the original graph, the original function at that upper limit. And as you can see in red, since now area is not a number, it's not 5 or 10, it's a function like we had in that example, then that function can be increasing, decreasing, has its maximum, has its minimum, concave up, concave down, and that's the most awesome idea you can think about. Because if this area indeed represents the number of sick people right now in the hospitals, we can find how fast this number is increasing or decreasing and prepare more hospitals if we need. That's exactly what happened during COVID-19 in China, when they calculated that they don't have enough hospitals, and they started construction of a new hospital. That new hospital was ready, I think, in 10 days, and it was a perfect time to use it. How did they know when they need this hospital in the future? They used mathematics to calculate the function of how fast the number of patients keep adding into the local hospitals and how soon we will need more buildings. It's pretty cool. All of this is thanks to mathematics and mathematical models. So let's all thank to math for surviving the world, in this world. That's a cool joke. In the next video, I will show you more examples, how to actually do your homework and to know how to differentiate integrals. See you next time.